This video is part 2 of a series about recovering the exact values of quadratic irrational numbers from their simple continued fractions. We'll discuss recovering the value when there are non-repeating terms before the first period in the simple continued fraction. We'll set up the problem and define a process for recovering the values, then we'll work an example. Let's get started. The problem we are talking about here is when we have a simple continued fraction that has some non-repeating terms and then has terms that repeat indefinitely. Generically, it looks like this: x equals a0, a1, a2, and continuing to some a sub n, and then r0, r1, r2, and continuing to some r sub n. The terms denoted by r repeat, so we say this simple continued fraction is periodic. The terms denoted by a do not repeat, so they make the simple continued fraction eventually repeating. What we want to do is find x, which will be a quadratic irrational number. To be more specific, we want to recover the exact value of x. We could calculate convergence, which would give us closer and closer approximations, but we want the exact value. Here are the steps in the process. First, find capital R, the purely periodic simple continued fraction that you get if you omit the non-repeating terms at the beginning. It just has the terms denoted by lowercase r. What you do is find the convergence for one full period, then solve for r using p sub n minus 1 plus p sub n times r all over q sub n minus 1 plus q sub n times r. We have a separate video about this if you are interested. The next step is to find the convergence for the part of the simple continued fraction that just has the non-repeating terms, the ones denoted by a. Then solve for x using x equals p sub m minus 1 plus p sub m times r all over q sub m minus 1 plus q sub m times r. That's it. Let's do an example. We'll find the exact value of 2, 2, 1, 2, 3, with 1, 2, 3 repeating. Here's the process we just outlined. First, we have to find r, the repeating part. To do that, we need to calculate the convergence for one full period. We won't go through this step by step, but here is the table like we use in other videos. Notice one full period is in the row for a. The convergence are in the rows for p and q. P is the numerator and q is the denominator. Please see this other video about calculating convergence if you would like more information. Now we have what we need to calculate r. It equals p sub n minus 1, which is 3, plus p sub n, which is 10, times r, over q sub n minus 1, which is 2, plus q sub n, which is 7, times r. After we do the algebra to simplify this, it is 4 plus the square root of 37 over 7. If you'd like to see that algebra worked out, please see this other video about recovering purely periodic simple continued fractions. This is the example we used in that video. The next step is to calculate the convergence for the non-repeating terms. We won't go through this step by step either, but here is the table. Notice we have the non-repeating terms 2, 2 in the row for a. The rows for p and q contain the convergence. And now we have what we need to solve for x. It is p sub m minus 1, which is 2, plus p sub m, which is 5, times r, all over q sub m minus 1, which is 1, plus q sub m, which is 2, times r. What's left is substituting in the value for r and doing some algebra to simplify. We'll work through this, but for those of you who don't need to watch, here is the answer. X equals 20 plus the square root of 37 over 11. Alright, let's do the algebra leading up to this answer. First, we'll substitute what we calculated for r into its place in the numerator and the denominator. Here's what that looks like. Now we'll multiply through by 7, which is in the denominator of r. In the numerator now we have 14 plus, and we'll also expand this. 5 times 4 is 20, and we also have 5 times the square root of 37. In the denominator we have 7 plus, and this time we have 2 times 4 is 8, plus 2 times the square root of 37. Do the arithmetic, and we have 5 square roots of 37 plus 34 over 2 square roots of 37 plus 15. We can simplify this. What we'll do is multiply the top and bottom by 2 square roots of 37 minus 15. In the numerator, we multiply this 5 and this 2 times the square root of 37, so that is 10 times 37 equals 370. And we multiply 34 times 15, so that's minus 510. And we have 5 times negative 15, which is negative 75, plus 2 times 34, which is 68, times the square root of 37. So that's negative 75 plus 68 equals negative 7 square roots of 37. In the denominator, we multiply this times this, that's 4 times 37, and we subtract this times this, That's 15 times 15. The other terms cancel. Do the arithmetic one more time and we get negative 140 minus 7 square root of 37 over negative 77. We can factor out negative 7, which leaves us with x equals 20 plus the square root of 37 all over 11. This is the answer. It is the exact value of this simple continued fraction. To check that the answer is correct, one thing you could do is calculate the convergence for the simple continued fraction. You'd find that they provide closer and closer rational approximations to this value of x, an irrational number. This gives us confidence the solution is correct. If you'd like to be completely sure, though, what you can do is expand this number back into its simple continued fraction. You would get this as the result. We won't do that here, but there is another video where we expanded this number into its simple continued fraction. Please see that video if you like to see it worked out. In this video, we set up a problem statement and gave a process for recovering exact values of periodic, eventually repeating simple continued fractions. Then we worked an example. That's all for now.